So we're going to do another example. We're going to determine the normal modes of methane. And so, this is a three-dimensional molecule. It's not just planar, so it's a little bit more difficult to visualize. So I encourage you to pull up a model of methane as we go through this video, or either in physical reality or on Otterbine's website, right? Tetrahedral molecule. So, this is molecule in point group TD. So that's always going to be the first thing to figure out in any problem we do, most problems we do in this course. And so first thing to do is pull up the TD character table, draw a Cartesian coordinate system, and figure out gamma stationary. Or you can do gamma XYZ first. Doesn't matter. We're just going to be multiplying them. And so running through, we have 5 different classes of symmetry operations. The first one's always the identity. When you do the identity, all of the atoms stay the same. And I've labeled these atoms hydrogen A, B, C, and D, and then the carbon. And so all 5 are going to stay the same. So we have a value of 5 for the first part of our reducible representation. Now we're going to do a C3. Now there's 8 different C3s in this molecule. And the beautiful thing is, right, because all of those C3s are in the same class, right, because they're listed together in the same class, it doesn't matter which C3 you choose. You're always going to get the same answer of there being 2 atoms that are stationary. Now, which atoms those are will change depending upon which C3, but it's not going to change your overall answer, which is just 2. So imagine you just rotate through this carbon-hydrogen bond, right? That's going to interchange HB, HC, and HD. It's like spinning the top of a tripod. And C and HA are going to stay stationary. So that's why there's 2. A C2 bisects any of the HC H angles. And so I can kind of draw that for you, or you can look at the Otterbein website again, or some other molecule, but that's going to go through there, right? So this hydrogen is going 180 degrees. So this hydrogen and this hydrogen, A and B, are going to interchange. D and C are going to interchange. So the only thing that's staying the same is the carbon. So that gets us a value of 1. Very similar one is the S4. The S4 has the same location of this. And so you're going to do a 90-degree. And so basically what's going to happen is the hydrogen is going to go to the center and then pop down. Again, that's easiest to see with a model. They will all interchange. All the hydrogens will interchange. So only the carbon stays the same. And then you have a sigma D. The sigma D, there's 6 of them. Probably the easiest one to see is this one that's flat in the screen here. And so that would be a mirror plane here, right? And so this basically angle, all of those atoms are in the plane. So those aren't going to move, HA and HB. And then HD and HC, which are HC is in front of the plane, HD is behind the plane, those are going to move. So since you have 3 atoms that are in the plane, that's going to get you a value of 3. Next, we have to do gamma XYZ. So we're talking about XYZ on the central atom. That's what we care about. And so let's see what happens here. So identity, well, X is going to go into X, Y is going to go into Y, Z is going to go into Z. So that's going to be 3. And in fact, for every single problem for the identity, doesn't matter the point group, gamma XYZ, it's always going to be 3. Start out with a 3. Doing a C3, okay. Well, the C3 is something where you have to think about this a little bit, right? And so here it is. Z is going to go to Z, right? So we're rotating along this portion. We're doing 120-degree rotation. since it's a 120-degree rotation, X, which is now moving, right, is not going to move, X and Y are not going to move to anything clean. It's not going to move to negative X, negative Y, nothing clean. You have to use your trigonometry, and the formula that we introduced back in chapter 1. And so that's going to be these cosines and sines. And so you're going to take the trace of this matrix, and cosine of 120 is negative half. So negative half plus negative half equals negative 1. So your total transformation matrix, right, would be larger than this. It's going to be basically all of these, right? Because you have X, Y, Z. So this is your transformation matrix for X, Y, Z for C3. You're going to have a 1 there, and then you have a cosine 120 and a cosine 120. And so when you take the trace of that, that will get you 0. In other words, I split it up into 2 parts here just so we can see it easier. Yeah. Now we can do a C2. A C2, we can define the C2 as going through one of these. Again, remember it bisects angle, so I showed it going through one of these axes to make it simplest. So going through the x-axis, it's a C2, and so that's going to make a y vector become negative y, right? And x is going to stay the same, and z is flipping, right? So the whole molecule is flipping. It's 180 degrees. So you got a negative 1, a negative 1, and 1. That gets you negative 1. S4 is, again, on the same axis as the C2. And so what's going to happen now, you're doing a 90-degree rotation, okay? So x is going to go into y. That's what's shown here. Again, there's an implicit xy here, right? And y would go into negative x. So that's what that showed. That portion there is going to get you 0, that 2 by 2 matrix. Z is going to go into negative z because you do a C4 and then you do a sigma h, right? And so overall, you're going to get the 0 contribution here, negative 1 contribution, giving you a negative 1 value down here. Last one is a sigma d. And so it looks like here, I defined it to be in the xz plane, okay? So that's going to interconvert this hydrogen and this hydrogen because the plane is right there, right? And so x and z, since they're in the plane, those aren't going to move, so that's going to give you 1s. And y is on one side of the plane, so it's going to go to the other side of the plane, become negative 1. Overall, that gets you a 1. So there's our reducible representation for gamma x, y, z. Now we have to multiply the gamma stationary that we found out earlier with the gamma x, y, z to get the gamma nuclear. And so we multiply all these values. 3 times 5 is 15, etc., giving us 15, 0, negative 1, negative 1, 3. And now all we have to do, remember, this is all the degrees of freedom of the atoms. So we have to subtract off the translational and the rotational modes. But before we do that, we have to reduce this reducible representation, use the formula we learned in chapter 2. And if you go through all that mechanics, which is just a bunch of math, arithmetic, it's not too bad, you're going to get that gamma nuclear is equal to A1 plus E plus T1 plus 3T2. You can see there was no A2s as it turned out. So now we have to subtract off the rotational and the translational. And you can see that the rotational, they're actually triply degenerate. This has a dimension of 3. And so these are all degenerate, and they all transform as a T1 symmetry. Similarly, the 3 degrees of freedom for translation, x, y, and z functions, all transform as a triply degenerate T2 symmetry. And so we're just going to subtract those out. And so the T1 is going to go away because we subtract 1 off, and then this, we're subtracting 1 T2 off. So that becomes 2T2. So we end up with the following normal modes, 1A1, 1E, and 2T2 modes. And now something very important, oops, there's a typo here. I should say triply degenerate. Something very important here is to remember that there's degeneracy to a lot of these modes, right? A1 is not degenerate, it's non-degenerate because it has a dimension of 1 there, but E is a doubly degenerate mode, and these T1 and T2s, those are triply degenerate modes. So we have one non-degenerate A1 mode, one doubly degenerate E mode, and two triply degenerate T2 modes. So we have a total of 9 modes, because 2 times 3 is 6, and then we have plus 2 for the one doubly degenerate, it gets us 8, plus 1 is 9. So how do you interpret this? So we can check this. We have 9 modes. Check it with the 3n minus 6 for a nonlinear molecule. We have how many atoms? We have 5 atoms of methane. And so 3 times 5 minus 6 is indeed 9. So that's all good. What does this actually mean? This means that we have, before we look at those, we have 4 different energies that these modes occur at, right? We have a certain energy for A1. We don't know what that energy is, but we know that's a unique energy. We have a certain energy for E, but within E, there's 2 modes that have the same symmetry and the same energy. The specifics of how the atoms are moving are going to be different, but it suffices it to say they have the same energy and the same symmetry. And then we have 2 sets of triplets, basically. Not triplets in terms of peaks, but just we have 2 sets of 3 modes, and each of those 3 modes have the same energy, okay? So very simply, if we don't consider overtones and other selection processes, we would expect to have 4 different energies where peaks could show up, right? The 2 different G2s, and then the 1E and the 1A, right? And so what do these look like? Just like before, we won't go over yet, we will later, how to derive these pictures. It's pretty cool. You can go from all this group theory stuff to actually going to these pictures. But just realize, right, that again, the symmetric stretch is looking very symmetric, right? That has the totally symmetric symmetry, A1. And then E, we have E happens to be a bend. Why is it a bend? We'll go into that later, how you can figure out if it's a bend or a stretch. But look at just how these kind of look similar. They're degenerate modes. The specifics of how the atoms are moving are different, but they have the same energy. So this would be embodied in one peak, right? And then, you know, my computer is pretty laggy with everything that's going on and all these videos it's trying to play. But you can see these stretches, okay? We have a bend. One of these T2s is a bend. Again, all these 3 T2 bends are going to be degenerate. That gives rise to one of the T2 modes. But we have 2 of them, right? And the second one is going to be stretched. So again, anything that's not A1, the traditional way in organic chemistry, right, is to call that asymmetric.